Hello, today we're going to be looking at section 4.1, which is about exponential and logarithmic functions. I don't have guided notes for this. You can just take notes on a regular piece of paper, and the examples will come from the examples in our textbook. Okay? So first thing we talked about, I know we already talked about exponential functions. Let me recap a little bit. Exponential functions are of the form f of x equals a to the x, okay, where a is some numerical value, okay, and x is your variable. So that's why they're called exponential functions, because the variable is in the exponent. A is also called the base. If you wanted to graph this, okay, so anytime you don't know what a function looks like, you can graph it using an XY chart, okay. So, and I always like to use the values -2, -1, 0, 1, 2, okay. And let's graph, for example, 2 to the x. So 2 to the -2 is 1 over 4. Okay, and let me draw the axes there. And 2 to the -1. Now x is -1, so that's, I'm plugging that into here, into here rather, and that is 1/2. 2 to the 0, anything to the 0 is 1. 2 to the 1 is 2, and 2 squared is 4. Okay. So to graph this, -2, it is 1/4. At -1, it's 1/2. At 0, it's 1. At 1, it's 2. And at 2, it's 4. 4 way up here. So you can see this thing grows pretty fast. Okay? And that's what an exponential function looks like. As x gets smaller and smaller, so as x gets more and more negative, the y value will approach 0. It will approach the x-axis. So it will never actually hit the x-axis, but it will approach the x-axis. So we call the x-axis an asymptote here, vertical or a horizontal asymptote rather. Okay. Let me scroll down a little bit. If your function looks like this, we call this exponential growth. Okay, when a is larger than 1, then we have exponential growth. Okay, we can also have exponential decay. When a is less than 1. Okay, and when a is, so when a is a fraction, right? When a is between 0 and 1, we have exponential decay. So let me do an example. Let's graph 1/2 to the x. Okay, again we make an XY chart. Let's use those same values. Now we have 1/2 to the -2. Okay, so that means we flip this, so that negative tells us to flip the fraction, and we get 1, whoops. So when you flip the fraction, you get this squared, and this becomes 4. 1/2 to the -1. Again, the negative tells you to flip the fraction, and you leave the exponent positive. It becomes 2. When x is 0, anything to the 0 is 1. 1/2 to the 1 power, first power is 1/2, and then 1/2 to the second power is 1/4. Okay, and let me graph this function. Let me graph this function in a different color on the same graph. Let's use green. Okay. So when x is negative 2, actually let me use pink, let me use a different color. When x is negative 2, y is 4, so that is over here somewhere. When x is negative 1, y is 2. When x is 0, y is 1. When x is 1, y is 1/2, and then 1/4. Okay, so exponential decay looks like this. Okay, so exponential decay, whoops, is in pink, and exponential growth is in blue. Okay. Let's do, before I get to the example, let's talk a little bit about compound interest. Okay, let me pause my video and make some more space on my page. Okay, let's look at compound interest. So there's some terms we have to define first. So the first term is abbreviated FV, which is called future value. So if you deposit money into an account, the amount of money after so many years or after so many months is called future value. So future value is the value after t years, and usually when we say t, we mean the number of years. Okay. Capital P stands for principal, which is the original amount, right? The amount that you deposited. It's also known as the present value. Okay. How much are you depositing now? How much did you deposit a while back? R is the annual interest rate. Okay, lowercase r. Annual interest rate, which is, you always want to write this as a decimal. Okay, so like 5% would be 0.05. And M, lowercase m, stands for the number of compoundings. Number of compoundings per year. Okay. So annually means you compound once a year. You could also compound semi-annually, which means twice a year. You could also compound quarterly, every 3 months, so that would be 4 compoundings a year. And then monthly and daily. Okay. So those are the number of compoundings a year. Now there's a formula we have for future value. Okay. So the formula that we have for future value, if you want to figure out how much money is going to be in the account after so many years, is P times 1 plus R over M to the MT. Okay. I think your book uses N. That's okay. I use M. That's fine. Okay. Let's do an example. Alright, so this is on page 261 in your book. The first example. Find the value of $4,000 invested for 2 years at 12% compounded quarterly. Okay? So we need to write down all the little bits and pieces we have. $4,000 is the initial investment, right? So that is our present value. That's P. invested for 2 years, so that's t, time t equals 2. 12%, so that's r. And compounded quarterly, that means m equals 4. So now all we have to do is just plug and chug, right? Plug this into the formula. P1 plus, and then I always like to write out the formula in variables first, and then go ahead and plug. So that is $4,000 invested, or I'm sorry, $4,000, 1 plus r. R is 0.012 divided by m, which is 4. And then 4, which is m times t, which is 2. Okay, so that is going to be 0.112 divided by 4. So what you can do in your head, you can. Otherwise, you can plug this whole thing into the calculator. So 0.12, so 12 divided by 4 is 3. Plus 1 is going to be 1.03 raised to the 8th power. Okay, and when you plug that into your calculator, let me show you how to do this the first time. So that's $4,000. Oops, what's going on with my calculator? Alright, I had to make some adjustments there. So that's $4,000 times 1.03 raised to the 8th power. Let me do this inside here. Raised to the 8th power. Okay. Now I have this fancy calculator that actually does this kind of type, math type, but if you just type in this up caret, it'll actually show up caret to the 8, and that's okay. Okay, so you get $5,067.08. Okay, so roughly $5,067. Now, what if I wanted to find out the amount of money that I need to deposit now, right? How much should I deposit now if I need $10,000 in a few years? Okay, so I'm going to take this formula, the formula for FV, and solve it for P, present value. Okay, so the formula for principal present value equals PV, which is FV, future value, divided by 1 plus R over M, whoops, raised to the MT. So all we did there was solve for P. Okay. Let's look at another example. So it says find the present value, and this is page 262 in your book. Find the present value of $5,000 to be paid 8 years from now at 10% interest compounded semi-annually. Okay. So I'm just going to use this formula here. So my future value is 5%, or I'm sorry, $5,000. Find the present value of $5,000 to be paid 8 years from now at 10% interest. Yeah, so the $5,000 is going to be paid 8 years from now. So that is the future value. To be paid 8 years from now, that's T, at 10%, so that's 0.10, compounded semi-annually. So we said semi-annually was twice a year, M equals 2. Okay. So then I have my formula, PV, let me just write it again here, equals FV divided by 1 plus R over M raised to the MT. Okay. So that's $5,000 divided by 1 plus 0.10 divided by 2 raised to the M times t. Okay, so that's $5,000 divided by 0.10 divided by 2 is 0.05. So 10% divided by 2 is 5%, plus 1 is 1.05. Right, the whole, and then 5% more, which is 1.05 raised to the 16th. Okay. If you plug this into your calculator, you'll get 2290.56. Okay. Okay, let's look at example 3, also from your book. A car worth $15,000 depreciates in value by 40% each year. How much is it worth after 3 years? Okay, so how much is it worth after 3 years? So you have to ask yourself, are we solving for the future value or the present value? Okay. Currently it's worth $15,000, so that tells me, okay, that's the present value. I need to find the future value. Given that the interest rate is 40%, but it's depreciating in value, that means it's losing money, right? So my interest rate is going to be negative 0.4. Okay, after 3 years. Time is 3 years. So I need to use the formula for future value. That's P times 1 plus R over M raised to the MT. Oops. So what is that? That is P, which is 15,000. 1 plus, the rate is minus 0.4, divided by M. Each year depreciates each year, right? So M is 1 times M to the M times T. T is 3. So that's negative 0.1, negative 0.4 divided by which is what? Oh, what is happening here? Okay, so that is 1 minus 0.4, which is 0.6 raised to the 3. And then once you plug that into your calculator, you should get roughly 30 to 40. Okay. So in 3 years, this car will be worth $3,240, even though today it's worth $15,000, right? So that's what happens with cars. They start depreciating the moment you drive them off the lot. Alright, so now let's suppose, instead of compounding monthly or daily, I'm done with that example. Let's suppose I compound continuously. Okay, so I'm earning money on that money in the bank continuously. Every time I earn a cent, it starts compounding right away, and it keeps compounding. Okay. So how many times a year do you think? So M equals what? How many times a year do you think it will compound? Okay. If it's compounding every second, every millisecond, we think something like 1 e to the 10th, right, which is 1 followed by 10 zeros. So there's a table in your book, which I have put here. So you can see this is a value of $1 after 1 year at 100% compounded M times a year. Okay, so if it's compounded once a year, then that dollar becomes $2, right? If it compounds 4 times a year, it becomes $2.44. If it compounds daily, it becomes $2.71, right? And as M increases, we get down to 2.71828. Where have we seen this number before? 2.71828. Okay, this is that magic irrational number E. Remember we talked about that last lecture? E equals 2.71828. ... right? It's an irrational number. It goes on forever. What is E? E, this is just for your general knowledge, E is actually the limit. when we get into limits, you will see that as m approaches infinity, it's 1 plus 1 over m raised to the m. Okay, that is what 2.71828, that's where that comes from. Okay, so that's just some extra knowledge. What you need to remember is the formula for continuous compounding. So for continuous compounding, okay, the formula for the amount or the future value is going to be P e to the RT, okay, or PERT. That's how some people remember it, PERT. So we're no longer using P times 1 plus R over M to the MT, we're using P e to the RT. Okay? Let's do another example. Before we do that one, let me write this one down. Okay, so this is find the value of $5,000 at 3%. At 3% interest compounded continuously. Okay? Continuously. So that should be a tip-off for you when you see that word continuously that you're going to use PERT, and that's for 20 years. Okay, so long time savings. So we're going to do P e to the RT. The principal, the current value is $5,000. E to the R is 0.03. Remember, we have to put it as a decimal. Raised times T is 20 years. Okay, and this you can plug into your calculator directly. Let me show you. Okay, so that was 5,000 PE, so it was E. So remember, second and above the ln is the E button. E to the 0.07 times 5, or times, how many years was it? Times 20. Oops, it wasn't 0.07, I apologize. It was 3%, right? 3%, yeah. 3%. $5,000, 0.03 times 20. Okay, what do we get for this? So 9110.59. Since we're rounding, we put this little squiggly equals, which means approximately. So that's how much money you can expect to have after 20 years. You start off with $5,000. You let it sit in the bank and collect interest. After 20 years, you have over $9,000. Okay. Now the question is, how much should I deposit now? So let's say I want $20,000 in 5 years. How much should I deposit now? Okay. So the formula for present value is, we can solve this here. It's the future value divided by e to the RT. Okay. Instead of using future value, your book uses A for amount. That's fine. Okay. Let me write it this way too. That's how your book writes it. And then you can also write it like this, right? Remember, when we have negative exponents, we can move those to the top. So you can write it like that, okay? And this is for continuous. Oops, continuous, UOUS compounding. let's do another example. Now I want to know how much should I deposit now? How much should I deposit now to have $5,000 in 5 years at 7% continuous compounding? Question mark. Okay. So how much should I deposit now? That means I need to solve for PV, the present value. Future value over e to the RT. I need $5,000 in the future, so that's 5,000 is the future value. E, the rate is 7%, 0.07. Time is 5 years. Okay? So when you plug that into the calculator, you are going to get roughly $33,523.44. Okay, and again I can show you how to do this. You're going to do 5,000 divided by e to the 0.07 times 5. Oops, I forgot the decimal. If that ever happens, don't delete everything. Just go back and do second DEL. Second DEL is insert. And it will let you insert that point or whatever you need to insert. Okay. And there we go. $3,523.44. Okay. Let's look at another example in the book. This is example 6. So examples 4 and 5 I wrote out, and this is example 6. Okay. So now you want to know, let's suppose I have $1,000, right? And the bank is offering me 2 different rates: 16% compounded quarterly or 15.8% compounded continuously. And I want to know what's the better bang for the buck, right? Which gives me the better return. So let's look at $1 for 1 year. 16% compounded quarterly for $1 for 1 year. So this is the formula P1 plus R over M raised to the MT, right? That's what this is. That's going to give me $1.17 at the end of the year. If I have 15.8% compounded continuously, this is using the formula PE to the RT. That's going to give me $1 and 0.171 cents, so a little bit more than 17 cents. Okay, so for $1 for 1 year, it's not going to make a difference. But if I have $1,000 and I'm compounding that for 10 years, that's going to make a huge difference. Okay, so 15.8% compounded continuously is far better than 16% compounded quarterly. So you have to be a wise consumer, right? When you go to the bank and they're offering a higher rate, doesn't mean it's necessarily better. You have to look at how much it's compounding, right? Or how fast it's compounding. So the actual percent increase during 1 year is called the effective rate of interest, the annual percentage rate, or the annual percentage yield, right? So the continuous rate of 15.8% is actually 17.1% as an annual percentage rate. Okay, the stated rate is the nominal rate. So nominal means name, right? What is the named rate? The named rate is 15.8%, but the actual percentage rate or the annual percentage rate is 17.1%. Okay, and in 1993, the Truth in Savings Act required that banks always state the annual percentage rate. So before then, you had to be a wise consumer and kind of figure that out yourself. Now you can always ask for the annual percentage yield or annual percentage rate. Same thing with credit cards. They are required to report the annual percentage rate of interest. Okay. So that's in general the applications of exponential functions. Let's look at just some exponential functions in detail. So this is different functions of e to the x. Remember last time we talked about e to the x. E is between 2 and 3. So if 2 to the x looks like this, or let's say 2 to the x looks like that. 3 to the x is steeper, it looks like this. E is between 2 and 3, so that's going to look something like this. Okay? But what happens if I have e to the 2x or e to the negative x? What does that do? Well, this is a bunch of graphs that show you exactly what happens, right? Notice that if I have e to the ax, as a increases, right, as a goes from 1 to 2 to 3, my graph gets steeper and steeper. And as e becomes negative, or a becomes negative rather, the graph flips and becomes exponential decay. And as the value of a gets larger and larger, so if it's -3 or 3, it doesn't matter, the graph is going to be steep. Excuse me, whereas if a is a fraction, then the graph will be more spread out, or the increase will happen more slowly, or the decrease will happen more slowly. Okay? So what I want you to do is work on some active learning problems. So this is the mathematical symbol for section 4.1. If you want some practice problems, you can work on roughly 10, 15, 39, and 46. Okay? Or you can pick some problems similar to that are odd numbers, so the answers are on the back of the book. And then, of course, work on your homework. If you have any questions, please feel free to get in touch with me. Okay, thank you for watching.